My name is Lyons, and I'm here to speak to you today about energy. And so we're all looking ahead to the smart grid of the future, and hopefully that's going to really start to kick in over the next year or two. A lot of legislative developments happening both in Europe and further afield, which is trickling into Ireland. So I'm here to give you a picture of hopefully what that smart grid is going to look like and how this product, SECO, is hopefully going to fit into it. So SECO stands for Smart Energy Cluster Optimisation. By a cluster I mean a company or an industrial estate that has both an amount of load, but is also integrated with the market, and also potentially is developing its own energy, generating its own energy. So we may have solar or we may have wind. Okay? So firstly, just a word about the TSSG. The TSSG stands for the Telecommunication Software and Systems Group, which is the research arm of the Waterford Institute of Technology. So basically I'm an engineer myself, and I spotted this gap in the market that we need an optimization platform that will allow you to optimize a renewable energy that you may have on source, which of course is intermittent and flexible by its nature, with a load on the other side that's potentially flexible. And I'll explain as we go on what I mean by flexible load. We also will integrate with the market in that the market price changes every half an hour, and obviously if you have some flexibility in your load, you should be ramping up when prices are cheap and ramping down or even stopping altogether when prices are expensive. So this graphic shows what SECO represents. And SECO obviously there is in the centre. So if you take the top left-hand corner there, which is the load. So if you have a manufacturing site, we'll say that may have some flexibility in how it consumes its energy. So we'll say for simplicity, you have a large cold storage company, and that cold storage company obviously has a thermal load, and you're switching on and off energy to keep that thermal load between a temperature band. So if we say, for simplicity, that temperature band is between -15 and -25. We will model that load such that we know the cause and effect. When you turn on 10% or 50% or 100% of your energy, your compressors and your evaporators, how much the temperature will drop. And when you switch them off to 50% or to zero, how much the temperature will rise again, and how much time that will buy you. I won't explain exactly now how the energy markets work, but suffice to say, the smart grid of the future is going to be using a lot of time of use tariffs to incentivize customers to use energy at particular times. You've probably all seen the spikes from the World Cup when everybody put on their kettle after the penalty shootout. Basically what happened there is the demand was so high that EirGrid had to switch on lots and lots of power plants to match that load, even though it was very, very temporary in time. The more they had to switch on, the more expensive those power plants were. So if you can think that a peak power station in the Midlands charged a lot for energy, they were being switched in to satisfy that load. And the last generator to come in will set the price for that half hour. So that's why you get these huge spikes in price. You can predict those, and our algorithms allow you to predict when they're likely to be. So, it depends on how much wind is on the system, how much load is on the system, a lot of complex issues. So if you have an idea of what your price is likely to be over the next 12, 24, 36 hours, and you've modeled your loads so you know when to switch on and switch off, we've developed algorithms in a system to switch on and off to suit your most economic time. Okay? You'll see in the top right-hand corner we have renewable energy there as well. So if you have renewable energy on site, if you have solar or wind, we again model what you're likely to get out of that solar plant or that wind turbine or number of wind turbines that you have. And again, the algorithms will optimize those such that you are economically getting the best from them. So there may be times when it's more economical to spill onto the grid because you're in one of those spikes, but most of the time you want to optimize it such that you are using your wind or your solar on site. So again, we predict how much we're likely to have over the next period, and the algorithms all work out what is the best thing to do economically for your plant. Okay? The fourth leg of the stool you'll see is storage and batteries, and the system can cater for that, but in reality storage technology is improving at quite a good rate, but still economically it's not economically feasible yet for normal companies to go out and buy battery storage, but that will happen. Again, if the system allows us to ramp up and to charge and discharge batteries to their profiles. So again, if you have a lot of wind and a lot of cheap power, you would store energy in that battery, and then when it's expensive or you have little or no wind, you would discharge that battery. So you're always trying to do the most economic thing for that cluster. Okay. Okay. So these are the problems that the smart grid of the future is pushing towards this new paradigm here on the right. Up to now, EirGrid are doing everything from a top-down point of view. They're trying to balance the supply and demand. So when you switch on a light or a fridge or a compressor at 4 o'clock in the morning, you expect the power to be there. EirGrid are there trying to balance that. Okay. In the smart grid of the future, there's got to be also a bottom-up approach, which gives control and intelligence to the end user. So whereby, if that end user can potentially switch on and off at times to suit them, then they're going to be using a lot of energy in the troughs, which is what an energy system wants. It doesn't want to be switching in really inexpensive power plants. So in the electricity system in the future, you have much fewer generators, but much more intelligence, but you also have to have a bottom-up approach for that. And that's what SECO is addressing. Okay. So our premise is that, yes, you need a lot of stuff happening at the top down, but unless you incentivize the end user and give them the intelligence to engage with the market, then the whole smart grid, that's when the whole smart grid will kick off. So why are we solving this? So really what we're doing is these clusters, these are little microgrids, the little smart grids on their own. So this little cluster is like a little microgrid. And that little graph there shows you the bar charts is the demand, and the blue line is the difference in price. So you can see the price can change by a factor of 10. So most of you, either in your businesses or in your home, are buying electricity at whatever 16, 17, 18 cents per unit at all times of the day. What's happening there is your supplier is buying it on your behalf at 4 o'clock in the morning if you use it, and selling it to you at whatever price you've agreed. But you can go on this wholesale market, which is every half an hour, and you can buy and sell on that. So if you're a big enough factory and you have storage on site, you should be using a lot of energy early in that day when the price was cheap, and using as little as possible when that peak is there. We can predict that when those spikes are likely to be and when those troughs are likely to be, and we then turn on and off your equipment to suit. Okay? So really what we're trying to do there is turn, up to now, energy users are very much just consumers. In the smart grid of the future, they're going to become prosumers, they're going to become involved in the energy market themselves, and they're going to allow arbitrage to buy and sell. Okay? So this is distributed generation, but distributed generation means when you actually generate power yourself. And up to now, if you have a wind turbine or a solar plant on your site, it's very hard to make it economically pay for itself. But if you were actually involved in trading on the market, your return on investment is much, much quicker, because you're potentially selling energy at a time when it's very, very expensive, and you're also displacing energy when it's very expensive on site. So you're allowed to buy and sell. So sell your energy when it's expensive, buy it when it's cheap. Okay? So that allows that end user with this intelligent site to become a playmaker, to become a prosumer. This is a simple example of a client, and on the left-hand side you see that their load, they're using between 2 and 3 kilowatts a day. So that blue line is their energy use on the 15th of January 2014. And the purple and red line down at the bottom is the price. One is the forecast. I mentioned that we can forecast this price, because all of this is ahead of time. That forecasted price is the red line, and the actual price, when everything was added up, is the purple line. So obviously it's very important that those two lines move together, the peaks and troughs move together. When we worked out their models, we found that we could have turned on and used a hell of a lot more energy at night. So the green line is their optimized load. Okay? Obviously when the price then starts to get expensive, we switch off quite a lot of load. And then when it gets really expensive, between say 4 o'clock and 8 o'clock, we switch nearly everything off. So the process in this particular case, they had enough storage to allow us to do that. So the green line and the blue line, we've used exactly the same amount of energy in that day, we just used it at different times. they're a very, very large energy user. They're using between, they have what we call an NYC, and maximum input capacity of 5 megawatts. Very, very large. If they were able to do that in one day, there's a huge saving in the region of €1,000 in that one day. Okay? To allow you to do that. So looking ahead to the future on the smart grid, there's what's called an energy trilemma. Everybody that's in regulatory are trying to bring in rules that solve these 3 issues. One is carbon emissions, the other is the cost, and the other is security of supply. Okay? By giving that control to the end user, you're answering all 3 of those trilemmas. Okay? So this is something that's very much about to happen in the markets over the next while. Solar is becoming much more affordable, and people are becoming much more energy conscious. So how do we put this into an industrial setting? As I say, first thing we have to do is we have to model what your loads are. We must know the cause and effect, because you cannot switch something off, someone's production schedule off, unless you know that you're not going to go outside their set period. So we have a rules engine in our system that keeps everything within those set bands. If you have distributed generation, if you have solar or wind, it allows you to bring that in and use it intelligently. Up to now, it's just if the wind blows, you have to try and use it on site, and you spill the rest onto the grid at a very, very small money. Whereas with an intelligent system, you can play the market. Okay? As this goes on, and hopefully we model these clusters, and we bring the supply and demand as close as we can together. And there's another cluster close by. The next step for this is that these clusters then begin to trade with each other. They don't have to trade with the market necessarily, but they can begin to trade with each other. And that's how these microgrids will hopefully roll up regionally and nationally, and then you'll have a really smart grid. So our route to market, as I said, I'm an engineer by trade, and I've come back into the WIT, the Water Institute of Technology, to develop this in the TSSG, because the TSSG had the skill set to do optimization platforms and optimize. I've done a lot of work in optimizing telecom networks, and we're doing the same now in optimizing smart grid. So at the moment we have a number of test beds going in industrial sites, some with distributed generation on site, others that are just linked with the market, and the results from them are quite positive. The next step is to bring it towards what we call virtual power plants, where these plants can start to trade amongst each other. And there's a lot of other mechanisms on the market, like demand-side management, which will bring all that together. So with that, we'll be bringing in storage, distributed generation, voltage optimization, ancillary services. And the last stage then is we hope to bring this to microgrid partners that we're speaking with in the UK, in the US, and in Europe. So as I say, the future of the smart grid is this new paradigm that I spoke about, where supply and demand are much, much closely met. There's this new wave of innovation that economists are starting to talk about, coming after the industrial age and the information age, that now we're going to have the low carbon age. Ancillary services and negawatts. Negawatts are incentivizing people to switch off instead of switching on their plants. And you need this type of energy intelligence to allow that to happen. As I mentioned earlier on, the hierarchy in the energy trilemma, it's all going to head towards dynamic tariffs, time of use tariffs, and incentivizing people when to switch on and when to switch off. So as I mentioned earlier, this is what the model we look at. I've spoken to you so far just about cluster one. Cluster one is optimizing that supply and demand, but then there's no reason that we can't then start to trade amongst other clusters, and then you really make these microgrids turn into a smart grid. As I said at the beginning, then these algorithms and platform were developed by PhD level software engineers in the TSSG, and the plan is that we will spin out this intellectual property from TSSG into a spin out company. We will hope to continue to work with TSSG and bring this to stage 2 and stage 3, which is good. So that's a very, very quick overview of the energy markets and how SECO sits into that. So, any questions? I'm around for the rest of the afternoon, or grab me outside here, or shoot them now. Hi, Mike.
Question. Do your algorithms take into account the response rate of people that are turning on and off, the latency or
So Mike was just asking there if if our system takes into account the type of equipment that we're using, the response rates of it. So we have a rules engine within our system that allows you to build that in. So I mentioned the example of a cold store, for instance. We would build in. You might save a lot of money by switching on and off compressors, but if you're switching them on and off every 10 minutes, then you're probably going to cause more mechanical problems. So within that, you build in your rules engine. So you might be that they can only come on once every 2 hours, and if they go off, they have to stay off for 2 hours. So you can build all those into a rules engine. So if you're dealing with other pieces of equipment like compressors, like evaporators, you can build that rules engine into the system. Any other questions? Anyways, thanks for your attention. And if you want to catch me later on, I'll be around. Thank you.